Welcome and thank you for downloading this TU Delft podcast.
Seat. Last week, or yesterday actually, I talked about climbing and descending flight. We made a start in treating the topic of climbing and descending flight. So the things I like to address today are, for example, if you have an engine failure, how far can you glide? Or perhaps if you want to climb to a certain altitude as fast as you can, then how much time is this going to take? If I can have your attention. So, climbing and descending flight performance. I made a start last time, and today I'm going to talk about 5 minutes or 10 minutes. I'm going to refresh your memory, what I treated before. And then I'm going to solve some actual problems. Is everybody okay? Finished talking to each other? That's better. So, a short summary of what you've seen before. Of course, we always need equations of motion to describe what an aircraft is doing. Now, you've already seen this picture many times, but we have 4 forces on the aircraft: thrust, drag, lift, weight. And since this is a 2-dimensional picture, it will result in 2 accelerations. One vertical, perpendicular to the flight path, which will make you pull up or push over. And one forward acceleration, which is related to an increase or a decrease of airspeed. Now this is just to refresh your memory. If you take that picture, then these are the 2 equations of motion that you end up with. Now this is the most general case, but today I'm simply going to talk about climbing and descending flight at a constant speed. And at a constant straight line. As you already see on the right-hand side of the picture, you can see the airspeed vector is in a straight line. So this means that, for example, a term like d gamma dt, it remains 0 because, simply speaking, gamma is constant. So what we learned last time was that the equations of motion, in that case, simplify to these 2. Thrust minus drag minus a weight component, which is pulling you backwards, equals acceleration, and lift is equal to weight. There was also another way of writing it. You could say, okay, I can take that top equation, and if I take the top equation and I multiply it with airspeed, then instead of forces, I obtain power. Now, this means that power, on the left-hand side, you can see excess power, which is basically the power you have available and the power you need to overcome aerodynamic drag. So that's energy you have in excess. That can be used for a term V sine gamma, which is the vertical component of the speed. So that's an increase in potential energy. And the second term is basically an increase in kinetic energy. So it's simply an energy relation. Now, today we're going to discuss climbing and descending flight. And the one thing you can say about that is that we do these climbs and descents at a constant airspeed. Because there will be one particular airspeed at which the aircraft flies most efficiently. So, let me just put these, if you say dv dt is 0, let me just put the equation on the board then, because we need it throughout the whole lecture. Then I get this one, and the other equation I get is that the excess power is equal to V sine gamma, which is called the rate of climb. So, in other words, I have one equation which tells you something about the angle gamma, so how steep are you climbing, and I have one equation that tells you about the rate of climb, which is basically the time it takes to get to a certain altitude. So these are the two equations we're going to use because we're simply flying at a constant speed. So if we then treat gliding flight, and I go straight. In gliding flight, we always assume, that's of course the most simple case, gliding flight, there is no thrust or there is no power. It's basically the same thing. So this can either be an engine failure or maybe you have a glider which doesn't have an engine in the first place. Now, that means that either this thrust term or this power available term becomes zero in the equation, and therefore the equations of motion even become a little bit more simple. Now, we've already discussed this question, how far can you glide with a Boeing 747 following an engine failure? Is this distance from 10 kilometers altitude, but hopefully at the end of the lecture you could calculate this easily in a minute or two yourself. So I'm going to skip this sheet because we discussed it. What I'm going to look at is the best gliding performance. Now there are two parameters I'm going to look at. One is to have minimum rate of climb, or actually it's a negative rate of climb, so rate of descent. So that's in terms of time very nice, because if you're in a glider just enjoying the view, then it's nice if you can stay in the air for as long as you can. The other option I'm going to look at is to have minimum flight path angle. So that means the angle at which you're going down is as small as you can, and in that sense you'll achieve the maximum distance. So if you look at option 1, time, then we're going to take this equation here. We simply say, okay, power available is equal to 0. So that means minus the power required, so the energy you need to overcome aerodynamic drag is equal to weight times the rate of climb. So in simple words, this means, of course, I don't have energy available from the engine. This simply means that all the potential energy I have is being transferred into kinetic energy, or in going down, in overcoming this drag. Now this is the first option, flying as long as you can. And for the second option, of course, we need this equation, because then we're interested in the angle gamma. We know thrust is equal to 0, so that also means that sine gamma is minus drag over weight. So that is an equation for the angle. So you can see straight away that for the second option, it's very nice to have minimum drag. And if you look at the first option, time, then it's very nice to have minimum power. So it's a slightly different thing, but they are related to each other. Now, these are the two things we're going to look at. Now, one thing you have to pay attention to is that the second or the first option so staying in the air as long as you can, time-wise, that's not treated in the book, so that's only present in these sheets. So let's treat these both things, and let's start with the most relevant one, trying to get as far as you can following an engine failure. So what we know, I've just written down this equation, since thrust is equal to 0. So the flight path angle is the arc sine of minus drag over weight. And due to the minus sign, you will always get a negative angle. Now, since weight is the same as lift, that's the second equation of motion, the flight path angle is minus drag divided by lift. And since drag and lift, if you divide the two, then drag is CD times a half rho v squared s, lift is CL times a half rho v squared s. So it's the same as saying that's the arc sine of minus CD over CL. Now that's all very nice. So this means you have to fly at the highest lift over drag ratio in order to get as far as you can, because that was that minimum drag condition. Now, we already solved that problem because we already know that drag coefficient is simply a function of the lift coefficient. So this is what we used to obtain this result. So we've done that several times for several cases, but the important thing to realize is that this lift coefficient is simply a function of a couple of constants. A zero lift drag coefficient, pi aspect ratio, which is a geometric aspect, and E, the Oswald factor, which describes how efficient the plane really is. So this is basically a constant for a given aircraft. If you know this constant, then you can fill it in here, and then you find the corresponding CD. So you can straight away, if you know pi AE and CD0, you can calculate CL over CD maximum, and therefore you can calculate this angle gamma. Now that's a bit messy, so let me remove it for you. What you see now is that once you know the lift coefficient, from lift is equal to weight, you can always calculate what is the corresponding speed. And that's something you can write down in the manual. Tell the pilot if you fly at that speed, you will reach the furthest distance in case of a gliding flight. Now, I'm not sure if you noticed this, but perhaps a question I can ask you. If I have a very heavy, let's say I take one aircraft and I make it very, very heavy, does that then influence the glide angle? Does aircraft weight influence the glide angle? So would gliding flight of a heavy aircraft be better or worse than the gliding flight of a not so heavy aircraft, so the same aircraft with not that much weight on board? I don't know who thinks it's A, couple of B, a little bit more, and C. Okay, well then, that's good then. I think B was a little bit more people here, and that's the correct answer. You can see it from the equation straight away, that gamma, the angle, does not depend on the aircraft weight. But that is a bit curious. So the question is, what does the aircraft weight do then? That's something you can simply write down in a picture. Because if you look back at the equation, of course the angle doesn't change. However, if you look at the airspeed relation, there is a weight in there. So this means that if you're very heavy or very light, doesn't really matter in how far you're going to fly. It does matter how fast you're going down, though. So the total magnitude of the vector, the airspeed vector, will be larger. So you'll get to the same distance, but the heavy aircraft will just go down like a brick very fast. But the lift over drag ratio determines basically at which angle you can fly. Of course, there's a limit to this. You cannot make the aircraft as heavy as you like, because that will also influence your stall characteristics or your minimum airspeed. But that's a different story. But it is a funny result. Now maybe a story which shows you that this is a relevant thing to calculate. This was a flight with a DC-9 you see on the left, so that's a twin-engine aircraft. It was flying from Huntsville to Atlanta. I don't know if you know the geography of the United States, but that's right through the area where there's lots of tornadoes and hurricanes. So on the day of this flight, it was also very bad weather. And what you see here, these different areas, they're basically areas of different weather. So the darker it gets, the worse it is. Now, this flight was going from Huntsville. It was going straight here. And in those days, the radars weren't that good. So the weather was so bad, basically, that the radar didn't pick it up anymore because it was just one big blur to it. So they thought that here there was an area of no bad weather, like you have here. And they thought, we have to go right through there. But, of course, that was a bad decision. So they flew right through a lot of thunderstorms, and the engines ingested a lot of water, which means about 50 or 30% of everything that was going into the engine was actually water. Now that shut down the engines. The engines were also damaged, and they basically came out of the thunderstorm with no engines operating. And of course they asked air traffic control straight away, okay, where do we have to go? Well, they said, okay, you should go to Dobbins Air Force Base. And then what the flight did was they flew in this trajectory, and it isn't completely clear what happened because the cockpit voice recorder didn't pick up everything. But pilots at some point thought maybe it makes more sense to land here at a small airfield or over here. And they were also trying to restart the engines. However, they came to the conclusion that in those airfields you couldn't land because the landing strip was basically too short. So they ended up turning around again to Dobbins Air Force Base. They didn't make it, and they landed on a highway. Didn't work that well because there are trees next to a highway where the wings are. So they ended up in a petrol station, and the whole aircraft broke in two. But the question really is, what if over here, when they came out of the storm with failed engines, would they have been able to reach this Air Force base? Now this is typically a question I could ask you on an exam. So these examples, they're also relevant for the exam. So just a couple of numbers. Aircraft is 90,000 pounds, 1,000 square foot, a bit of stupid numbers here, but that's the wing surface area. It has a certain drag coefficient, that's zero lift, and a certain Oswald factor describing how efficient the aircraft actually is. Now, Air Force Base was 36 kilometers away, and the altitude at which they were flying, because it was relatively short distance, they were only at 7,000 feet, that's 2 kilometers, or a little bit more, when they actually had the failure. Now the question is, would they have made it? Answer yes. Would have been a stupid question if they weren't able to do that. But this shows you how you could actually calculate this for a given aircraft. So we basically know that the most efficient lift coefficient to fly at for CLCD's max is this one. So if you know a bit about the aerodynamics of the plane, you can simply calculate, okay, this will result in a lift coefficient of 0.68, and from this we can calculate with the parabolic lift drag polar what the actual CD value is. So that's 0.04. A lift coefficient always has to be much larger than the drag coefficient, otherwise you've done something wrong in your calculation. But once you know these two values, you can simply calculate this angle. So you should get a negative angle, and in this case it's minus 3.4 degrees. So if you know this angle, and if you know the altitude, then you can calculate simply what the distance is. So it's a fairly simple thing to calculate yourself, if you have some information about the aerodynamics of the plane. Now, so much for gliding flight, trying to get as far as you can. I've also talked about this other option, where instead of the angle, the rate of climb is important. So we know if power available is 0, then the rate of climb multiplied with aircraft weight is equal to minus the power required. So from this, you can say, well, power required is equal to aerodynamic drag multiplied with airspeed. And we know, now we have two unknowns here. So have a look at what is drag and what is airspeed. Now, from lift is equal to weight, we know drag equals this. And we also know from lift is equal to weight what the airspeed relation is. So if we multiply these two, we get the equation for the power required. And that's simply this thing. So multiply 2 and put everything underneath the square root, and that's what you get then. So if you want to stay in the air for as long as you can, so have a minimum rate of descent, so these are meters per second, then power required must be minimal. And from the equation you can see straight away that this factor here should be also at its minimum in order to achieve the best rate of descent. Now, not sure if you remember, but that's also something we already solved for the other problems we treated in the lecture. If you remember, minimum power required gives you that ratio of CL and CD, and again you get some kind of a equation for CL because the drag coefficient is a function of CL. So all these things here, they are constants. So again, this is a constant value. And again, you can calculate the speed, well, it's over here, the speed that belongs to that particular CL value. So these are all calculations. You can also put them in a graph. You can see straight away, if you plot forces, then the minimum drag condition is where you like to fly. So that's this speed over here. And if you look at power, then this here, bless you, is the minimum drag condition, and this would be the minimum power condition. So hopefully you now realize that gliding flight, you will find the same kind of speeds that you find in horizontal flight performance when you try to achieve maximum range or minimum fuel use. So they're the same type of speeds and parameters we're looking at. Okay? So much for gliding flight. Now let's have a look at climbing flight. And of course, during a climb, you will have thrust and you will have a certain power available. So these would then be the equations that you need. And again, if you try to climb time-wise as efficient as you can, you have to look at this rate of climb equation, because you're talking about the speed. And if you look at how steep can you actually climb, then you have to look at this equation, which has the angle in it. So it's basically the same problem as with gliding, but now we have a fixed value for thrust or power. So, okay. So in general, this was the picture we have. So we have a power equation, and what I've drawn over here is a very general performance diagram. Now, we're making these assumptions about jet aircraft, about propeller aircraft. In real life, there aren't nice straight lines. It could be anything in between. This could, for example, be a turbofan engine, which behaves a little bit different. So this power available curve can look like anything basically, but it will always start at zero because you have zero velocity there. But what you see, if you make a diagram like this, and this could be the most general case for a given aircraft, then this difference you draw here between power available and power required, that's basically this measure here. So that distance tells you how fast you can climb. So you can see straight away that if you fly very fast, then you cannot climb that quickly. If you fly very slow, you cannot climb that hard. And somewhere in the middle over here, where the curves are the furthest apart, that's where you can climb the fastest. That's where you have the most energy in excess. So, what am I going to talk about? Two things. I'm going to treat the maximum rate of climb for a propeller aircraft and the steepest climb for a jet. And what I'm not going to treat is maximum rate of climb for a jet or maximum angle for a prop. So I'm not going to do this. And why am I not doing that? The reason is simple. There is no analytical solution to it, so you cannot simply write it out on the exam. However, if you have this picture for a given aircraft with either power or thrust, then you could easily read it from the diagram. But let me show you the two solutions for maximum rate of climb and the steepest climb for a jet. So if we start with the first one, then I've just shown you that this excess power can be used to climb. So this distance here tells you how fast you can climb, and it basically says that if you want to climb as fast as you can, so I want to have this RC maximum, then this thing must be maximum. So the difference between power available and power required must be at its maximum. Now you can see in this diagram that's over there. In this diagram it's somewhere over there. And we're going to look at propeller aircraft. Now for propeller aircraft we always say, okay, power available is more or less constant. And the reason we do that is because this propeller can adjust itself to the airflow. It can adjust the blade pitch of every propeller blade to the oncoming flow, like I treated in a couple of lectures before. So power is constant. Now if power is constant, you can see that wherever power required is at its minimum, that's where you'll achieve maximum rate of climb. So again, this is more or less the same as this rate of descent issue. Again, you can climb the fastest way time-wise when you fly at this airspeed for minimum power required. And again, you get this relation of CL/CD and a particular CL condition. So again, same solution, and you'll see every time we come to the same type of answer to all questions. And now this is the solution for a propeller aircraft. And now let's have a look at jet aircraft. So now the issue is not time, but the issue is how steep can you actually fly. So steepest climb, and the objective of course is that this is the airspeed, this is the angle. So gamma should be maximum in order to, for example, miss the mountain. Now, if we go back to this equation, then it says that thrust minus drag equals weight sine gamma. So you can also say that the excess thrust that you have, the more thrust compared to the drag, divided per unit of aircraft weight, that gives you the sine of the flight path angle. So for jet aircraft with a pure jet engine, we always assume that this engine isn't really affected by how fast it is flying. So the engine thrust can be assumed more or less constant. And if I would devise an exam question, I would always tell you, okay, you can assume that the thrust is independent of airspeed. But you can see straight away that if you want to have gamma maximum, then that means that thrust minus drag must be maximum as well. Now, since thrust is a given value, then the maximum is found where the difference between the two is the largest. So that's the minimum drag condition. Yeah? That's a V, yeah, that's right. So this is thrust or drag, and the x-axis is airspeed. So you can read straight away what's the airspeed, and again, as we already seen, that for minimum drag you should have maximum lift over drag ratio. Again, that same CL value, which is a matter of constants basically, and if you know that, you can calculate airspeed. So hopefully you'll see that every problem is more or less the same, but now we can also treat climbing and descending flight. Then an example calculation. This is typically what I could ask you to do on the exam. So you'd get some information about a given aircraft, and you have some information about the power of the aircraft, and then the question could be, what is maximum rate of climb? So what you would have to do is you'd have to derive these equations of motion. You would then have to fill in the numbers, figure out which lift over drag ratio is relevant, and basically find the corresponding airspeed. Now, I'm not going to treat it now. That's a lot of writing, but the whole solution to the question is in the sheets, and I will put them on Blackboard later today. So you can practice that at home, if you like. So that's all about climbing performance and descending performance. And what I'm going to do now is, I've treated horizontal flight, I've treated aircraft climbing and going down. The only thing I'm going to look at now is what is the effect of, for example, the altitude. Does it make sense to fly high or low? Is there a question? Yeah. Well, if you know the speed and if you know the lift coefficient, then you can immediately also calculate the actual drag, right? So we always calculate CL and airspeed. Now, if you know CL, you also know the drag coefficient. So that means I can calculate aerodynamic drag. And if then this thrust value is given, you can calculate the actual angle. So you must know the thrust before you can answer the question. Yeah. Okay. So, next topic is basically the flight envelope. Now, what is the flight envelope? You won't see this many equations anymore. If I can have your attention again. Flight envelope is not really about the calculations we've done before. I'm just going to look at, okay, I've calculated how fast can I climb, how fast can I fly, how slow, and what I want to end up with is basically a diagram with altitude and airspeed, and there will be some region where the aircraft is able to fly. So I'm going to look at what happens as a function of altitude with the performance of the plane. Does it make sense to go fly high, or does it not make sense? So this is the main objective. So, short summary of the previous lectures, 2 diagrams summarizing everything you've learned so far. Then I'm going to look at altitude effects, so what happens with air density to all the relations. Then I'm going to look at what does that do to the performance. And I'm also going to talk about some operational limits. Now, even though the aircraft may be able to fly very fast, it could very well also be that then the wings would break off or something else would happen. So there are several operational limits, structural limits of the aircraft which cannot be exceeded. So I'm also going to treat those, and combined with what the aircraft can actually do, that will give you the total picture of aircraft performance. So, just the summary before the break. This is basically everything I've told you before. So, if you look at the performance diagram, then all the important points can be summarized in the diagram. So, what happens? So, I have minimum speed, that's where the drag curve stops, basically. Then, at some point, here I'm talking about forces, I have a minimum power condition. Now that's where you basically have the minimum rate of descent in case of engine failure. So this is for a jet aircraft. Then there's a point of minimum drag, which is of course interesting if you want to climb steeply, descend steeply, or stay in the air for as long as you can, endurance. Maximum range for a jet is achieved at a slightly higher speed, so there's a trade-off between speed and distance. And finally, the maximum thrust depends on the thrust that the maximum speed depends on the thrust that the aircraft can actually generate. So this is all summarized for a jet aircraft, all the important speeds at which you could fly. And you can make the same diagram for a propeller aircraft, and you get a similar picture, but now it's with power on the y-axis, and you see the same kind of things: minimum speed, maximum endurance, maximum rate of climb, rate of descent, maximum range, small glide angle, and a maximum speed. So all these points, they are things you can calculate now with just basically these equations of motion and some information about the propulsion system of the aircraft. Now, I think, let me just show you what this lecture would then be about. Now, up to now, I've only considered an aircraft flying at a certain altitude. But I want to know what happens if you fly higher. Does the performance become better or worse? So how is this affected? And a nice example is in fact this U-2 airplane. Now I don't know if you know how high it can fly, but it can actually go up to 21 kilometers. And this was already in the 1960s, so that's pretty high. It's twice as high as conventional civil aircraft fly nowadays. So we'll look into these kind of things. Not everything in this lecture is in the book, so look at the sheets. The relevant paragraphs in Introduction to Flight are listed here. But again, have a look at the sheets first. So that's all for this hour. In the next hour, I'm going to look at altitude effect. Okay, so what I'm now going to talk about is basically we've already done the calculations for all the parameters that we want to calculate. So we can calculate maximum range, maximum endurance, steepest angle, minimum rate of descent, and so on. The only thing I'm going to do now is I'm going to look at what happens to the aircraft performance as a function of the altitude. So does it become better or worse? Now, the key to all the calculations was this performance diagram, because you could summarize everything in one diagram. So all I'm going to do now is I'm going to look at what happens to the performance diagram if I change the air density, which up till now we kept constant. So what you have to realize is that at low speeds, the aircraft is flying at a fairly high angle of attack. So if you have a small speed, you need a large angle of attack, and if you fly very fast, then you have a lot of dynamic pressure, half rho v squared. So this angle is then small. And what you have to realize is that lift coefficient is a function of the angle of attack of the aircraft. So each point in a diagram, at each airspeed you have a different lift coefficient. So each point on the diagram relates to a certain angle of attack, a certain lift coefficient and a certain drag coefficient. So let's just assume that we take one given angle of attack and see what happens to that black point in the diagram. Now, drag. Of course, we know drag is CD over CL times the weight. Now you can see straight away, if you look at that equation, that drag, if you look at altitude 1 or altitude 2, so H1, altitude 1, H2, altitude 2, there is no air density in the equation, so the drag at both altitudes is exactly the same if we keep this angle of attack constant. So that means CL is constant and also the drag coefficient, which is a function of angle of attack, is constant. So that's interesting. So drag remains exactly the same, even though I changed the air density. Now let's have a look at what happens to the air speed. Of course, it's a diagram with drag and speed. So if you look at the airspeed equation, then in the airspeed equation, of course, there is an air density. So if you go to a higher altitude, so let's say altitude 2 is larger than altitude 1, so that means air density in 2 is smaller than air density in 1. So that means if that V2, so the speed in point 2, must be larger than the speed in point 1, because this CL is what I'm keeping constant. I'm considering a constant angle of attack. So that's very nice. So basically we know what is going to happen to the top diagram, because we know what happens to drag and we know what happens to speed, and those are the two things in the diagram. And I'll show you in a minute what happens to the point. What I also have is a power diagram, but power is directly related to drag. So it's simply multiplying drag with speed. So what you see then, if you look at the diagram, this point, drag remains the same, speed increases, so for a higher altitude, that point just goes to the right in the diagram. It shifts to the right. And you could basically do the same for each point on the curve. Now, if you look at power, that simply follows from speed and drag. And again, I'm going to consider a constant angle of attack, so constant lift coefficient, constant drag coefficient. Then, don't look at the equation, just look on the left-hand side here. Power is drag multiplied with airspeed. So, if I would divide these two, then drag is constant, so I get power in altitude 2 divided by power in altitude 1 is the same as the speed in altitude 2 divided by the speed in altitude 1. Now, what does that mean? What happens then to this point in the curve? It is going to travel upwards and to the right. And why is that? If you, for example, you'd have a certain speed here. Let's say I double the speed, then this equation here also says that I also have to double basically this power. So that means that the ratio of power and speed remains the same, so that's why you're traveling along this line. So what does that mean? That means the whole drag curve is going to shift to the right, and the whole power curve, all the points are going to go upwards and to the right. So this is a diagram for an actual aircraft, and now you see curves for several altitudes. So it starts at 0 meters in the international standard atmosphere, and we go up to 9,000 meters. So the drag curve is simply shifted to the right, and the power curve is going upwards and to the right. And that's what happens to aerodynamic drag and power. So that's fairly straightforward. But of course you can imagine that this has a consequence for what happens to the performance of the aircraft. Now this is what happens to the aerodynamics. The other factor in the story, of course, is the actual what the actual engine can do, so how much thrust or power you can generate. So let's just see what happens to the thrust of a jet aircraft. And just, you see equations here, but you don't have to memorize this kind of thing. This is just to give you an understanding of what's going on. What I'm plotting in this diagram is a thrust ratio as function of altitude. And T0 is the thrust at sea level. So let's say at sea level you can generate a certain amount of thrust. If you then go up in the atmosphere, higher altitude, then clearly air density is reduced and the temperature also reduces. Now, as you may remember, an engine creates a force simply by accelerating mass. So if the air density becomes less, then you have a smaller mass flow through the engine, so you get less thrust. If you want to memorize it easily, then once you get into space, there's no air left, no thrust. The other effect is that if you go up in the atmosphere, temperature actually reduces. Now, an engine relies on the fact that in the combustion chamber you put a lot of fuel into the air, you ignite it, and then you get high energy air which wants to accelerate. Now, if you have this combustion chamber, of course, is made out of materials, and they have a maximum temperature at which they can operate. Now, this means that if you put very warm air into an engine, then you cannot put that much extra energy into the air, simply because you'd reach the temperature limits of the engine. So in cold air, you can insert a lot more energy in terms of fuel, so you can also create a lot more thrust. So this means that temperature actually has a positive effect. As it gets colder, the engine can create more thrust. So this also means if you take a given aircraft and you place it at the North Pole, then you can generate much more thrust. On the other hand, if you would be in the desert, somewhere in a hot place, then you cannot generate that much thrust anymore. So these two things have an effect, and typically speaking, now this is just kind of an empirical relation, but the thrust compared to the thrust at sea level will depend on the air density compared to the air density at sea level, and perhaps there's some extra factor in there. So all I'm saying now is thrust reduces when you go up in the atmosphere, and of course at 11 kilometers altitude the international standard atmosphere changes a bit, and suddenly temperature remains constant. So how the engine behaves change a little bit then. But all you have to memorize is that, okay, if an engine goes up in the atmosphere, it can create less thrust. Now, for turboprop engines, you can say more or less the same thing, because the thing that drives the propeller is a gas turbine, and it functions in the same way as a jet engine. So don't look at the formulas. All you have to understand basically is that power actually reduces when you go up in the atmosphere, simply because air density becomes less. So having said that, we basically now know what happens to what the engine does, less thrust, less power, and we know what happens to the aerodynamic drag. And those two determine what the performance of the plane is. So combined, this is just a picture of a real aircraft. You see some power curves, so the power the engine can generate as a function of speed and the power required. And you can see that this power available as you go up in the atmosphere goes down, and these power required curves, they go into that direction. So let's just have a look from a qualitative point of view. What does this actually do to all the important parameters like minimum speed, maximum speed, range, endurance, climb angle, and so on. And everything together will give you certain performance limits, so those are the limits the aircraft cannot exceed. Now, minimum airspeed. Of course, the minimum airspeed that depended... Sorry? Minimum airspeed, of course, depends on this maximum lift coefficient. So it's basically where the power or the drag curve stops. You cannot go to the left simply because you cannot generate more lift coefficient. So this would be the minimum airspeed at altitude 1. Now let's see what happens if I go up in the atmosphere and these curves start to change. Now the power reduces significantly if I go a lot higher, and I've shown before that this is just a qualitative diagram, but the curve goes up and to the right. I should have actually drawn one in between, which is maybe somewhere over here. So minimum airspeed and then power. So what you see straight away is that this minimum point, because the curve goes to the right, actually shifts to the right. You can see it in the equation as well, that if the air density goes down, then the minimum airspeed goes up. And at some point, like I've shown here, actually these curves start to intersect. So this means that even though this point here is the aerodynamic limit, actually you cannot generate enough power to fly in that speed. So at some point when these curves start to intersect, you don't have enough power anymore to fly at the minimum speed. So you cannot go to the aerodynamic limit anymore. But what you have to notice from here is that there's an aerodynamic limit and there's also a power limit, and minimum airspeed obviously increases with altitude. Now, if you would draw that as a function of altitude, Then at sea level you might have some kind of a minimum airspeed, and of course it goes gradual to the right once you go higher in the atmosphere, and at some point you get limited by what the engine actually can do. You simply cannot fly at the aerodynamic limit anymore due to what the propulsion system can generate. Now this is what happens to minimum airspeed. We can do the same kind of thing for maximum airspeed. Of course, maximum airspeed is when the available power equals the required power. So it's the point all the way on the right in the diagram. But now let's look what happens if you change the altitude. So, like I said before, the power goes down, less power available, but the curve also shifts to the right. So, in this scenario I've drawn here, actually the maximum speed becomes a little bit less. But you can see that there is an influence in how much this power available actually goes down. So, if it wasn't that dependent on altitude, maybe this would have been the maximum speed. So, clearly maximum airspeed will change, but it depends on how much the engine force varies with altitude. So it depends on the engine characteristics and altitude whether or not maximum speed will decrease or increase. Now, I've talked about minimum speed, I've talked about maximum speed. Now let's have a look at the thing in between, which is the speed at which you can have maximum rate of climb. Now, I hope you remember, but all the energy you can have in excess, you can use actually to climb to create potential energy. So power available minus power required per unit of aircraft weight gives you a rate of climb. So in the diagram, this means that this distance between the two curves, this is basically a measure for rate of climb. And you could do that for any speed you like. So if I would draw the rate of climb you can achieve as a function of speed, then it looks a bit like this. So at the maximum speed, power available is the same as what you require, so you don't have any energy in excess to climb anymore. And that's logical, because if you would have extra energy, you could also accelerate a bit more. So you can see straight away from the diagram what the climb performance is of the aircraft. But once these curves change, if you go higher in the atmosphere, then power available goes down, less power from the engine, and the power required curve shifts upwards and to the right. And you can see straight away that these two curves come together, so the distance between the curves becomes less. So this means that this rate of climb thing I've drawn here goes down. So if the altitude goes up, then the achievable rate of climb goes down. Now, this is again for the actual aircraft, the performance diagram, and based on that diagram you can draw curves with rate of climb. So over here you can read how fast you can climb. So at sea level you could climb 9 meters per second, whereas at 9,000 meters you could actually climb maybe only at 1 meter per second. So this also means that at some point, if this is the performance diagram and this is the power required curve, then at some point the power available, so at high altitude, drops below the power required curve, and that means that the aircraft doesn't have enough energy to fly at that altitude. So then the rate of climb is less than 0 and you cannot get to that condition. So if you would take all these maximum values of rate of climb, then you could plot them as a function of altitude. So at sea level, so on the x-axis, you can climb very good, and when you go up in the atmosphere, the climb performance becomes less and less. Now, at some point, this is called the absolute ceiling. That's where your climb rate, which you can achieve, is 0, and that's the highest point you can fly at for a continuous matter. So that means in a diagram, then if this is the power required curve, then power available curve will just hit it in one point. Now that's kind of a theoretical point, because that's one airspeed at which you can fly, and if you would accelerate, decelerate a little bit, you would start to descend again. So this is called the absolute ceiling. In practice, an aircraft has a service ceiling, which is a little bit below, and that's actually the point or the altitude at which you can fly practically. So where it is possible for a pilot to get. Because you can imagine, if the climb rate is very low, like centimeters per second, then it would also take hours before you get to that theoretical ceiling. Can you all pay attention, or are you like talking to each other? Now, this is just a short story about an aircraft that can fly very high. This is a U-2. I don't know if you recognize it, but it's capable of flying at 21 kilometers altitude. And the idea is that in order to fly that, if you fly that high, back in the 1960s, you could actually, if you flew over Russia, they couldn't shoot you down, because all their aircraft couldn't go up to this altitude, and the surface-to-air missiles couldn't hit it. So you could simply fly over Russia, take some pictures, and fly back. Now, this worked very well for a few years, until the Russians managed to get to the altitude. And of course, some people like that, but this meant that the plane was shot down by the Russians. The pilot was safe, but this caused an international accident or incident, and it basically deteriorated the feelings between Russia and America. But what is nice to see is to look at the performance of this aircraft. So, in order to, if you remember, what we can say is that the thrust compared to the thrust at sea level is related to the air density and the air density at sea level. Now this is just an indicative equation. I'm just, if I take this equation just to show you why this aircraft actually looks like this, then I can also say, okay, air density is basically thrust times rho 0 divided by T0. Now these things are constants, and of course thrust must be equal to drag. So this says that rho is drag times a constant. That's CD over CL times a constant. So if you want to get this air density as small as you can, so you're flying at very high altitude, then basically CL over CD must be very large. So we have CL over CD maximum, which meant that we had this value of CL. And if you would then calculate, okay, what is CL over CD? Then CL over CD would be square root CD0 by AE. Of course, CD is this thing. And we know CL, so it's CD0 plus CD0 by AE divided by pi AE, which is 2CD0. Now, you don't have to do this yourself. All I want to show is that this parameter shows you how high you can fly. So you can see straight away that in here, if this A is very large, then that means you can fly higher. So you can see straight away that this plane is almost like a glider. It has very long wings for a given surface area. So it behaves like a glider. And if you would try to put this plane down on the ground, actually you have to do a lot of effort to get back on the ground because it keeps on floating. Furthermore, that's another story. These engines, of course, had to be designed such they could operate at very high altitudes. And that's not so simple if you want to prevent fuel from being frozen and being able to burn it properly. So, let me see, 15 minutes. What I have now is I can now combine everything I know as a function of altitude. So, if I combine all these limits I've discussed, then if I plot altitude versus airspeed, then on the left-hand side I have this stall limit. And at some point it was limited by the power of the engine. Now you can also draw the maximum speed, which is depending on what the engine can do. And these 2 points intersect at some point. And at that point your minimum airspeed is the same as the maximum airspeed. It's the same as the airspeed where you have maximum rate of climb, maximum flight angle. Everything is together into 1 point because the performance diagram looks like this. There's only 1 point you can fly at, so that's optimal in terms of all kinds of performance. So this whole region is basically where you can fly. Those are all the combinations of altitude and airspeed at which you can fly. Now this is clearly a performance limit, so this tells you what the aircraft can do. This doesn't mean that this is what the aircraft should do. So that's something I want to treat as well, some operational limits of the aircraft. So these can be things related to the structure, air traffic control, and so on. So there are a couple of things you have to take into account when you design an aircraft. And one is the fact that you must consider that you will encounter turbulence. So you will, this number here, 25 feet per second, that's simply based on statistics. Every so many flights, you will suddenly get an upward gust of wind of 25 feet per second. So let's say you were flying happily at airspeed V, then if you suddenly get this upward wind, then that means suddenly the aircraft sees a larger angle of attack, right? So you get upward U and airspeed V, and due to this U you get an increase in angle of attack. And since CL is a function of angle of attack, the lift coefficient will also increase straight away. Now, that is an issue because an aircraft is always designed to fly, to be able to fly at a certain load factor. Now, load factor is simply lift divided by weight. So this basically means if lift is larger than weight, and you would be sitting in the plane, and let's say lift is twice the weight, then you would feel twice as heavy because the plane is pushing through your seat. So this load factor tells how many G's the aircraft is pulling, basically. Now, you have to design an aircraft, so you have to specify a maximum load factor, which for example, for general aviation aircraft, like the one drawn there, could be 4. So this aircraft will be able to withstand load factor 4 before things will start to break down. Now, of course, due to this gust of wind, you get extra lift, and extra lift compared to the case at which you were flying, when you were flying at lift equal to weight, so load factor of 1, this will cause a load factor increase. So the change in angle of attack is basically the relation of the upward speed, which is specified by the airworthiness regulations, and the airspeed at which the plane was already flying. So the change of angle of attack is basically given as a function of airspeed. Now this means that the change of lift coefficient, that just depends on the steepness of this slope. So that will be something a little bit less than 2 pi. That's a given number for a given plane. So the change in lift coefficient is then this thing, and the change in lift, of course, is delta CL times a half rho V squared S. So the change in load factor is then delta lift divided by the weight. Now, if I work that out, you don't have to memorize this, just try to understand it a bit, then you get this relation here. So change in load factor depends on CL alpha, it depends on this vertical speed of the gust, airspeed and aircraft weight. Now what you have to realize that pretty much everything in that equation is constant. So this says that delta N is a constant multiplied with rho times V. Now this delta N is in fact also a given parameter. An aircraft can withstand a certain load factor increase, for example 3G. So you see straight away that the maximum speed at which you can fly depends on the air density, and it looks something like this. So as the air density goes down, the maximum speed goes up according to this relation. So that is basically a limit. If you go beyond the limit, then a gust of wind might damage the aircraft. Now this black line here, that's the actual limit. Of course, you don't want to risk flying at the actual limit. So there's always a safety margin. So this is what VD is, what I would call design diving speed. So that's the real limit. But then VMO, MO stands for maximum operating speed. So there's a slight difference between the two speeds. And that's just for safety. So there is apparently a maximum speed which you cannot exceed due to the fact that there will be upward gusts of wind. Another thing which is important is the Mach number. Now you've probably all heard stories about Mach numbers, about the sound barrier and so on. The thing that's important to understand is that if this is a profile, and let's say you're flying at speed v, then of course the air is actually accelerating over the wing. So even though you might be flying subsonic, at some portion on the wing you might have actually a region where you have local supersonic flow. And this causes basically shock waves and so on. Now, that creates a lot of drag, and I'm not going to discuss all of that in this lecture. But what also happens is that if you start to go very fast, then actually the point at which the lift is acting on the plane gradually shifts a little bit. So what you will start to feel if you go very fast, you start to buff it, and the nose might go up, it might go down, simply due to the fact that basically the lift of the aircraft acts at a different point. But what may be even more important is something else, and that is, of course, at the back of the plane you have the elevator, and of course you want to deflect that thing up and down in order to control yourself. Now, if you fly at very high speeds, then at some point a deflection downwards could actually cause a shock wave over here, which means that in some cases, without going into the details, these Mach effects can make the plane become uncontrollable. Now, that's something they figured out with this plane. This was one of the planes that tried to go beyond the sound barrier, and they couldn't control it. It experienced this tuck under behavior and pitch up behavior, and it crashed simply because the pilot couldn't control it anymore. And the other aircraft shown here is the first plane to go past the sound barrier, and this actually had a tailplane which could move as a whole. So it didn't have an elevator, but the whole thing could tilt. Now that's not so important for this lecture, but what is important is that at some Mach numbers, high Mach numbers, actually you get undesirable flying qualities. So these are things we haven't discussed, but there will be a limit to the Mach number which you don't want to exceed, simply because the plane can become uncontrollable or you experience a lot of vibrations. Now, that Mach number is a given value, and if you plot it as a function of altitude, then of course airspeed, this Mach number is fixed, it's a maximum. Air density, or the speed of sound, changes if you go up in the atmosphere, and this is why the limit, the Mach limit, actually changes like this as a function of flight speed. At some point you've reached 11 kilometers altitude. There is where the temperature remains constant, so speed of sound also remains constant, so then a given speed is a given Mach number, and this maximum value remains at this limit. So that's another limit, Mach number, which brings me to the final limit. Of course, if you go to high altitudes, you like to sit nicely in a pressurized cabin, breathing air like you do in here. Now, pressure outside the plane is much lower than inside. So you have a large pressure on the inside, a low pressure on the outside of the fuselage. So this causes the fuselage to expand, you get stresses in the structure, and a plane is simply designed for a certain flight altitude. So beforehand you decide, okay, this plane is never going to go beyond 15 kilometers, so I don't have to design a fuselage which has to go beyond that value. So this means that there's basically, if you look in the altitude airspeed diagram, there's one upper limit which is related to a certain air density. That will give you a certain pressure difference on the fuselage, and you're not allowed to go beyond that due to structural reasons. So those were basically the limits in terms of operational limits, and if you combine all of these, you get what is called the flight envelope. So I have here this limit which was related to gusts of wind. I have a Mach number limit, and of course the lowest of the two limits counts. So combined this will give you a boundary which you're not allowed to exceed. Then of course you have an altitude limit and an aerodynamic stall limit, and everything together this gives you what the aircraft cannot exceed. Now this is all related to what's allowed to do, but and they are fixed boundaries. So these boundaries will never change. However, the performance of the aircraft can also depend on what the propulsion system is doing. It may depend on the aircraft weight, all kinds of factors. So the actual performance, maybe it looks like this. So maybe the plane can do more than the actual plane is allowed to do. So these are two different things you have to take into account. Then one final story before I stop. What's important to realize is if you have limits, like a power limit, then this region over here, actually there's a whole small region of airspeeds that if you accelerate a little bit, you might hit a maximum Mach number. If you go up a little bit, you hit the ceiling of the aircraft. And if you decrease airspeed a bit, you're almost at the stall limit. So that's a very difficult region to fly at, because there's only a few airspeeds at which you can stay. Now this is an example of a TW8 flight from New York to Minneapolis. And if you look at this diagram, then the aircraft basically has devices at the front and at the back to create more lift. Now, this plane was put into a holding, so it should fly around there for a little bit because they had to wait to go to the airport. And what the pilots did was they thought it was a little bit beneficial to deflect the flaps slightly. They figured out that they could gain a little bit in terms of fuel use. But what happened is, when they tried to retract these high lift devices, so they tried to put these two devices back into their normal position. You can see there are many of them along the wing. Then actually one of them, number 7, I can't read which one it is, but let's say this one, it failed. So it remained at its original position. So this aircraft, because you create different lift on one side than on the other side of the plane, it started to roll and start to accelerate, and it went beyond this Mach limit. Now beyond the limit, it wasn't able to control the plane anymore, so the plane was spiraling down. Pilots were trying to do anything they could, but they couldn't control the plane. They reduced speed brakes and so on, nothing helped. Fortunately, at the end, the pilot got the idea to basically put the landing gear down. Of course, that creates a lot of additional drag, and that helped to slow down the plane and basically to get back into the flyable region. Of course, it was going nose down, so they had to pull up, and in the pull up they pulled 6 Gs. So they landed safely, but the whole plane was bent and several passengers were a little bit annoyed. But this shows you that this diagram is actually really relevant. And next time, before I stop, next time, if you just sit down a little bit for 1 second, treated everything about aircraft performance now. In the next lecture, I'm going to show you an example exam question. And finally, one particular thing. If you look at this limit, stall limit is actually a function of speed. And you may wonder if that poses a problem to the pilot. So I will treat about 10 minutes about air instruments, how that is actually solved. But that's all next time.
Please visit our Open Courseware website for more information. See you at our next podcast.